All right, this video is going to be a little bit of a long one to go through the entire process of solving, but bear with me because there's a lot of key steps here that are going to be really critical going forward to understanding mass and energy balances. So in the last video, we talked about setting up the problem, and in this problem, I'm going to run you through how to solve. So my biggest recommendation for this particular video is that you pause as you need to because I'm going to keep moving through the problem, and if there are key points and key takeaways that you need to write down, take the pause to make sure that they're ready to go. So, first thing we're going to do to solve this problem is we're going to write out any additional relevant information that we need in order to solve. So, we were given specific gravity and we don't have molecular weights, but we could look them up. So remember that whenever we have volumetric flow rates, we're going to want to get the volumetric flow rate into a mass flow rate because you can't balance volume, you can only balance mass or moles. So remember that your specific gravity is the density of the thing over the density of water for most part, and we want to know the density of the mixture of benzene and toluene. So what I've done here is I've solved for the mixture density using the specific gravity and the density of water. That's all that number is right there. Then I also looked up the molecular weight of benzene and I looked up the molecular weight of toluene. I will give these to you on an exam, but on your homeworks, you might have to go and look some of these up to get some practice. So that's step number one. Let's write out any relevant information that might help us just so we've got our numbers ready to go. The next thing that we're going to do is we are going to write and simplify the general balance equation. So the GBE, not the GBB. I have an extra letter there, but that's all right. We have three things we're going to balance. We can have an overall balance on the whole system. We can balance benzene as a species and toluene as a species. Now, for this particular problem, the balance ends up being the same for all three. And if you need to convince yourself of that, take time to make sure that you understand that it's the same for all three. So I'm kind of skipping a step and not doing each individually. So here's the general balance equation. Input minus output plus generation minus consumption equals accumulation. No reactions are occurring. This is a mixing system. So this is no generation, no consumption. And we can assume that this system is steady state. That's a fair assumption. So accumulation is zero. That means that the input is going to equal the output for all three balances that we have. So for the overall balance, the benzene balance, and the toluene balance. So there's the general balance equation. Next thing that we do is we want to write out our balances, simplify and solve anything that we can where possible to have really, really easy balance equations to work with. So the first one that I'm going to write is the overall balance. So overall, we have input equals output. So if we take a look back at our flow diagram, MEM1 is coming in and M2 and M3 are leaving. So M1 is your input, M2 and M3 are outputs. So this is the overall balance equation, and I put a little star next to it so that you remember that this is one of the equations we're going to use. Okay, the next thing that we could do is we could say, well, M1 is related to the volumetric flow in 1, and we already found the density of the mixture, so maybe it would be good to get a value for M1. So that's what I'm going to do. I'm going to take the density of the mixture that I found, I'm going to multiply it by the volumetric flow rate, and then I'm going to quickly check my units, right? So I'm going to assume at this point in the class you're checking your units. Meters cubed and liters are not the same unit, so you need a factor here, and that's important. Okay, and that's going to give me a mass flow in 1 of 1,744 kilograms per hour. So that's just making my life a little easier. I only have M1 right now. I don't know M1 and M2. I'm sorry, M2 and M3. Not yet, but I do know what M1 is, so that's going to make my life a little easier. So that's the overall balance. Let's write the benzene balance. So benzene, same idea. We have benzene coming in and benzene coming out. We only have one input stream and two output streams. Now remember that we can rewrite this in a different way. We can rewrite this equation and say that the fraction of benzene in 1 times the total mass in 1 is the same thing as the mass flow rate of benzene in 1. That's what this is saying right here. Okay, if this is still not clear, please come and see me in office hours. This is a really clear, critical concept. So that's all I've done for each of these, is instead of writing it as MB1, I've written it in terms of the composition and the total flow rate because it's easier, remember, to look for total flow rate because we have the equation above, and most of the time we're given composition. So we do know something about the composition of benzene, and we do know something about this mass flow rate 1. So what I'm going to do is I'm going to plug those numbers in. We know that that stream is 45% benzene, and we just found that M1 flow rate. So if we simplify, we can get down to this equation right here. And there's a little star, which is not that easy to see. So let's write over that. This is another key equation for us. So that's another balance. We can also write a toluene balance, and it's got the same general format. Toluene in 1 input coming in is equal to the 2 combined outputs, the output in 2 and the output in 3. We can do the same thing and translate that into a fraction of the total. And then we know what's coming in is 55% toluene, and we know that mass flow rate in, so we can simplify this equation. And what you'll notice here is we don't have xt2 and we don't have xt3, but up here we have xb2 and xb3. And we know that there's a relationship between these, right? We know that xb2 plus xt2 is equal to 1, and xb3 plus xt3 is equal to 1. So we could here substitute in, instead of xt2, 1 minus xb2. And that's another way of removing extra variables you don't know and replacing them with things that you might know or you might find out or are in other equations, because you want to have everything in similar notation. So that gives us 3 balances: an overall balance, a benzene balance, and a toluene balance. But right now, we don't have enough equations. So we need to move on to another sheet of paper to start to solve. So let's move things around here. So right now, too many unknowns, not enough equations. Okay, so that means we need another equation or a relationship to solve. So remember how in the setup video we talked about there's 8% B in the feed? Output 3 is 8% of the benzene in the feed. So what's important about this is we're only talking about benzene flow. So what this is saying is it's saying that the benzene in stream 3 is 8% of the benzene in stream 1, not the total of 1. So we need to be careful of our substrates. This is only the benzene in stream 1. Now, lucky us, we know that the mass flow of benzene in 1 is equal to the composition times the total flow. And we actually know both of these variables. So we know that the mass of benzene in the third stream is going to be 8% of the composition, which is 45% times the total flow rate. So we know that the mass flow rate of benzene in 3 is 62.8, and it's kilograms of B per hour. And that's important. It's not kilograms per hour. It's kilograms only of B. So this number is going to help us. So let's go back to our benzene balance, right? We know that mass of benzene in 3 is equal to the fraction of benzene in 3 times the total. And if we go back to our benzene balance, that number is hanging out right here, right? So this whole thing, this right here, is 62.8. So we can actually simplify just a little bit further and get a better equation going forward. And now we've only got 2 variables left in this benzene balance. All right. Now, one of the things that we have to be careful about is that we have moles in stream 2, but we don't have mass. And we have mass in stream 1. And everything in the problem is asking for mass. So we need to change what's going on in stream 2 from moles to mass. So this is where it gets important to think about your basis of calculation. We've been thinking about basis of calculation as only the input, but that's not the only place that you can assume a basis of calculation. You can assume a basis of calculation of 100 moles in the overhead product in stream 2. Now, what does this allow us to do? Well, this allows us to say, well, 95% of that 100 moles we just assumed is benzene. So that means that we have 95 kilomoles of benzene. So we can now have an N sub B2 equal to 95 kilomoles. By the same token, that means that we'll have 5 kilomoles of toluene. And I have the wrong subscripts right here, so let's make a quick fix, right? This should be a T3, excuse me, and this should be a B3. Nope, I apologize, a 2. We're in stream 2, right? Got to make sure our subscripts are correct. There we go. All right, so now that we've made our fix, right, what can we do now that we have an N? Well, we know If we have N, we can find M using molecular weight. So what we can do is we can say, well, if we have 95 kilomoles of B, and we know that the molecular weight of B is 78.11 kilograms per kilomole, that means we have 7,402 kilograms of B, which means now that we have MB2. Okay, now we're in the right area, right? We've got mass of B2. Let's do the same thing for toluene. Let's take the 5 kilomoles of toluene, multiply it by its molecular weight, and get 461 kilograms of toluene. And then remember that your fraction is equal to the component divided by the total. So the total mass that's in 2 is going to be the mass of benzene plus the mass of toluene, which means that we have a mass 2 of 7,881 kilograms of mixture, and that's the total mass. Now, if you remember, mass fraction is component over total. So we can now actually find the component X sub B2 that is in that stream. So let's do that. Let's take the 7,420 kilograms of B and divide it by the total mass, the 7,881. And we now know that the fraction of benzene that's by mass is about 94.2%. We also know that the fraction of toluene has to be 1 minus that. So we actually now know the fraction of toluene. So now we actually know a lot more about stream 2, and that's going to allow us to solve for everything else in the problem. So if we go down, we now have enough information to solve. Let's go back to the benzene balance. We got it down to this number equals the fraction of benzene in 2 times m dot 2 plus 62.8. We just found that number. It's the 0.942. So now we can solve for M2. This is one of the things that we were looking for. We want to know what's the mass flow in 2. So let's look. If we rearrange and we solve, we find that the mass flow in 2 is 766.5 kilograms per hour. There's something that we were looking for. Now that we have this mass, let's go back to the overall balance. The overall balance said that M1 equals M2 plus M3. Well, we already know M1. We just found M2. So we can find M3 by saying M1 minus M2. And what we're going to find here is that M3 is equal to 978 kilograms per hour. Finally, we wanted to know the composition in 3. We now know that the mass in 3B was equal to that 62.8. We just found M3 as 978, so we now know that the composition in stream 3 is only 6.4% benzene, which means that toluene is 93.6% of that final stream. There are all 4 numbers that we needed to solve for. So you can see that this is a very complicated problem. We start out by looking at what information we have, then we write our balances, then we do our best to use relationships to solve for things. Once we've solved for numbers, we can go back and plug into our balance equations to find the numbers that we're looking for. So again, this was a pretty long video, so if you need to go back through it at any point and take a look, please pause. And then what we're going to do is we're going to come back to this problem in a later video and do a degree of freedom analysis to show you that this is solvable. All right. There are multiple ways you can solve this problem. This is the most straightforward and the most streamlined approach, but you can solve this in many different ways. So there's our solution for this particular problem. We'll talk about degree of freedom analysis on this problem in another video.